Let's look at NMR, but we are going to do this is a typical question that is about 7 marks or more that is a combined analysis. Okay, so this is normally the data that you are given, and I want to summarize what we use this data for. The elemental analysis by mass allows you to find the empirical formula. Okay, so I hope at this point, empirical formula you're confident with, because you get to do it so many times in every question, right? So we get the empirical formula. Extremely important is the mass spectrum, okay? You're either given, like in this question, just the mass to charge ratio, which is 127 in this case for this question, or you're given the full mass spectrum, okay? Remember, the mass spectrum gives you the molecular ion. The molecular ion is the heaviest in the mass spectrum and corresponds to the molecule not fragmented. Okay, and remember it's a molecular ion, so let's revise that it's always +1 charge to be detected in the mass spectrum. The important thing is, though, is that it gives you the molecular formula, so please be confident in the calculation of molecular formula from the empirical formula. Then you are given the infrared spectrum. Once again, you could be given this as a table with the key wave numbers, or the actual spectrum where you need to, of course, recognize. And remember, the key thing about the infrared is that it gives us the functional group, information on the functional group. Okay, so I know we actually, you know what, it's relatively simple. And some peaks you are familiar with because they have a very distinctive shape. So just a little reminder here, for example, the alcohol, it has this like broad peak at the very left-hand side of the spectrum, okay? Or there are some others that are a little bit unfamiliar. Like in this example, you have one around 2000. This is something that you don't really explain you directly, but you have the data sheet. Okay, so the datasheet, it can be helpful after you do the first analysis to see if you actually recognize the functional group. In fact, notice here we have the datasheet of the infrared. Okay, but look how confusing it can get. So don't overanalyze it. First, see if you recognize the peaks, and then you can look at the datasheet if you don't recognize them. Okay. Proton NMR is the best technique to find the actual structure of the molecule. Okay, and I know it's difficult because apart from having all of this information of molecular formula, functional group, and then we have to build up the molecule, okay, we can really observe 4 specific things of the NMR. And if you don't mind, I'm going to go through it very briefly, just so that you just refresh it. So because remember, I do simplify things. This is what we look for in the NMR. The number of peaks gives us the chemical environment. The chemical shift, it gives us how close a proton is to the electronegative atom. The splitting pattern gives us the structure of the neighboring atoms, and the integration, it gives us the number of hydrogens, or well, let's stick to hydrogen because it will do proton NMR today, that are responsible for that peak. So we only look for these things. So I would highly suggest you to keep this in mind and maybe make a little revision card or use these revision cards, because this can help in doing the full analysis, okay? So to make it nice and organized. Now, of course, there are some questions about the reference, the number of peaks. Remember that we only look at hydrogen, we're looking at proton and NMR, so let's not get confused with the carbons. I know that's a common mistake, okay? And of course, we look for symmetry. So if there is symmetry, some peaks will appear in the same position, so the integration number would be higher. This is an important thing, okay? This task, we can do it for you. The chemical shift, okay, I won't go into detail, but remember, it's how close these hydrogens are to an electronegative atom. The chemical shift, you're given the data sheet with all of the part per million numbers. But again, it can get confusing. So sometimes you don't even need to look at the data sheet. First, try to do an analysis of, okay, I have these functional groups, I have these peaks, so which one is going to be the closest? Okay, sometimes you don't even need, because you know the functional group that it's present, okay? So don't rely too much on the data sheet. It can get confusing, okay? So first, do this analysis, okay? Then we said we have the splitting pattern. The splitting pattern, well, I do like to do the explanation of it, because it's why is a peak splitted into like a two 3, 4. It gets confusing, right? And the reason is due to experiencing spins of the adjacent proton, okay? But I won't go into detail now. Just remember the rule n+1. And the important thing is that like this, you get the structure of the neighboring atom. And the integration, it's super important, but you're not always given it, okay? When they want to make your life more difficult, they don't give it to you, yeah? And you're just given the peaks, okay? But otherwise, it's very important because it tells you exactly the number of hydrogens responsible for that peak because it's calculated, from the instrument as the area under the curve, okay? And you can be given it in different ways. So either actual numbers like these 3 to 2 to 3, which, well, it makes sense, isn't it? It's like CH2, CH3, the most common groups. Or you could be given it as little lines like this, and once again, the size corresponds to the ratio. Or maybe you could be given a a ratio that is not a full number. And that's a little bit more like a bit less straightforward, but then just like you do in the empirical formula, you would find the full ratio, okay, by dividing the smallest number, yeah, each of these by the smallest number, and this gives you the full ratio, okay? Anyway, don't want to explain it too much, but if you have an integration with small decimals, you still need to find the full ratio to get the number of hydrogen. Okay, so little summary here, but I am going to skip here to the carbon NMR because I would like specifically to show you this method, okay? Empirical formula, molecular formula, we're not going to do it right now. I think I think it's okay. The functional group, okay? I want you to look at the infrared spectrum for a moment and see if you recognize, without looking at the data sheet, if you recognize a functional group. So the important information that we got so far are the empirical formula, which is C6H9NO2, and the infrared spectrum peak of carbonyl and the nitrile, okay? We worked it out by recognizing one of the major peaks and looking at the data sheet for one that is a bit more unfamiliar, okay? But now we're gonna get to the analysis of the NMR, because remember, these questions are about 7 marks and you have to find the structure of the molecule, okay? So let's do it, but from now on, I would like you to learn to do the analysis of an NMR in a very nice and structured way, okay? I'm gonna do it very quickly, just so you have the overview of my method, and then you would stop the video and try it yourself, and then you can, and then see if you work out the structure, okay? Now, the first thing that I would highly suggest you to do is look at the integration data, because this is the simplest one, okay? With integration data, so, use the values to determine the number of hydrogens in different environments within the molecules, okay? This is relatively simple. We have CH2, CH, CH3, and CH3. Write that down. It's so important that you do it in a displayed formula, okay? Please. Displayed formula, and I know I don't always want you to do displayed formula like for mechanisms and things like that, no, but in this case, yes, absolutely, very important. So integration data, displayed formula. Second step, look at the splitting pattern and work out the neighbor of each of these peaks, okay? Because this is from the splitting pattern, and this is what I've done in this, but I would like you to try it on your own as well. Third step is to recognize the neighbors, okay, and the fragments, because now it looks like we have a massive molecule with so many carbons, but you have to do this step, which is recognize if the fragments that you wrote are the same, okay? Because one peak gives you the neighbor, and then that neighbor will be another peak, if that makes sense. So 2 peaks is normally 1 fragment if they're neighbors. So make sure you write it down and you look at them, because the next step is the very important one, that you only write the main fragments that you worked out. And the other step is, and look at this yellow line, it's extremely important. You would have to recognize that attached to that carbon, there are other things, because carbon wants to have 4 bonds. If it doesn't have all of the hydrogens and carbons attached, it means that there is something missing. And guess what? Your functional groups. So the last step, well, not the last step, but you would have to analyze the chemical shift. So you have to identify the peaks in the NMR that correlate with specific types of atoms, to say it in fancy words. And this is when you can look at the data sheet if you want. Otherwise, just at the relative position. Here, we have the empirical formula. We need to keep this in mind. And you know the functional groups, which means that your final step would be to put it all together into an actual structure. So, summarizing, we have integration data, splitting pattern, recognize the neighbors, and always everything in a displayed formula. Then write down just the fragments, and then figure out, okay, there are some bonds missing here. Let me see the functional group that I have. Let me see my fragments. I look at the data sheet, and then I work out, like, what are the remaining attachments. And I think this method can really, really help you working out the structure. And now it's your turn to write it down in your paper, okay? And I'm going to make a little note on the screen to remind you of these 4 steps. Okay, now is your turn. Summary of the method, the empirical formula, the molecular formula, functional groups. And now it's your turn to try to apply it. Okay, so I hope you gave it a go. So if you've replayed these videos because you want to look at the solutions. Okay, so I hope you followed my steps, and the steps we got 4 different peaks. So we have 4 different environments, 4 different hydrogen environments. Okay, then we looked at the splitting pattern, and we have these specific fragments, which we narrowed down to 2 specific fragments. So this is where I want you to take a moment and compare with your notes. Did you get these 2 fragments correct? Okay, remembering that, you know, each of what they correspond to, but I think that you can just relook at your notes. And then the analysis of the chemical shift. Okay, that's where we are at. And I showed you here the data sheet, so just the 2 key parts. Okay, but then I also, the most important thing that I think most people miss out is that you have the fragments, and then you have some missing bonds. So really what you have to do is just to put it back together. Okay, because you may think, okay, but how there are so many like molecules that can fit together? Well, what if, you know, the analysis that I would do, I would even ignore the data sheet. I don't like it. It confuses me unless it's really necessary. 1 bond here. This, I've highlighted it because it's the one that is the most shifted downfield. This means that is the closest to the electronegative atom. Which atoms do we have? Well, we have 2 oxygens, so we must have like this. And we don't have an OH because we looked at the infrared. We would have got it there. So it must be just a carbon, oxygen, carbon bond. We have a carbonyl because we found that before, and the nitrile. How do they come together? Well, this is the most shifted downfield. It must be connected to the oxygen. Okay, then we can't put this carbonyl directly, you know, like just we can connect it with the oxygen, because otherwise there is no way that we can fit everything together. And this guess where it could be? Well, this one is also a little bit shifted downfield, but a little bit less, meaning that it will be close. And notice also the data sheet here does help. It must be next to the carbonyl. So in the pink, I will highlight this bond. Okay. And then notice that by highlighting the different connections, you have 1 bond that is missing. What is missing? Well, the bond to the nitrile. So the final molecule should look like this. We have and I'm going to do also displayed just to keep it. So we have CH3. CH2 is this fragment on the left, connected to an oxygen. So we have an ester group, there we go. And then we have a CH, and this CH must be connected to the nitrile, and then we have a CH3. And this is our structure.